Welcome back to the Explainer. So if you're ready to bridge that gap between theoretical network protocols and the kind of hardcore, mathematically driven problem solving you're actually going to face on exams, well, you are absolutely in the right place. Today, we're diving deep into a transport layer masterclass. We're going to move from the really elegant logic of selective repeat right into the real-world nuts and bolts of TCP. So get focused, because we're about to break down the math, trace through actual packets, and crush some classic exam scenarios together. Let's get into it. Okay, let's dive into our roadmap for today. First, we'll look at selective repeat logic. Second, variables and formulas. Third, tackling the exam. Fourth, contextualizing TCP. And finally, routing and delivery. Starting right off with Part 1, selective repeat logic. Now, as you know, when hosts communicate over a network, the underlying paths can be totally chaotic. Packets get delayed, they arrive out of sequence, or they just drop entirely, right? So to provide a reliable service, our transport layer desperately needs a strategy to recover from these errors without grinding the whole system to a halt. Historically, older protocols like GoBackIn use something called cumulative acknowledgement. Basically, if a packet goes missing, the receiver just ignores everything that comes after it. That forces the sender to retransmit the lost packet and literally every single packet that followed it. It's incredibly wasteful. Selective repeat, on the other hand, does exactly what its name suggests. It introduces selective acknowledgement. Instead of a blanket retransmission of everything, the protocol specifically targets and retransmits only the missing frames. A real game changer.
So let's look at the actual operational logic on the receiver's end. When the receiver gets a frame that's out of order, meaning the sequence number isn't what it expected next, it doesn't just panic and throw it in the trash. Instead, it runs a quick check. If the sequence number belongs to the expected sequence number range, meaning it fits perfectly within our receiving window, the receiver actually buffers that frame and sends an acknowledgement for that specific frame. But if the frame falls outside the expected range, it's just treated as a duplicate. It gets discarded, and a duplicate acknowledgement is sent back. Honestly, this buffering capability, it's the absolute heart of selective repeat.
Moving on to Part 2, variables and formulas.
Now that we've got the logic down, it's time for the math. Because let's face it, network engineering isn't just hand-wavy theory, it's precise calculation. We're going to pull our base values from a classic GATE 2014 exam scenario. Let's explicitly define them first to, reduce our cognitive load before we hit the heavy formulas. Okay, so our packet size is 1 kilobyte, which translates to 2 to the power of 13 bits. Our bandwidth is 1.5 megabits per second. The one-way propagation delay, that's T sub p, is 50 milliseconds. And our ultimate goal here? To achieve a link utilization or efficiency of exactly 60%. Okay, so to find the transmit window size, let's call it n, required to hit that 60% target, we rely on a core formula. Efficiency equals n multiplied by the transmission delay, all divided by the total cycle time. So, first up, we find that transmission delay by taking our 2 to the 13 bits and dividing it by our 1.5 Mbps bandwidth. That gives us 5.461 milliseconds. Now for the total cycle time, we just take that transmission delay and add 2 times our 50 millisecond propagation delay, which totals 105.461 milliseconds. When we plug all this back into our formula, setting our efficiency to 3 over 5, right, 60%, we solve for n. That's 3 times 105.461 divided by 5 times 5.461. The result? 11.58. But obviously, we can't send a fraction of a frame, so we take the ceiling. N has to be exactly 12 frames to hit our utilization target. But here's the thing, knowing the window size is only half the battle. We still have to design the packet header to actually support it. For selective repeat to function without sequence numbers overlapping and confusing everything, the total number of distinct sequences has to be at least n plus n, or just 2 times n. Since our window size n is 12, we need 24 distinct sequences, ranging from 0 all the way to 23. To represent 24 unique values in binary, we just take the base 2 logarithm of 24 and take the ceiling. That tells us we need a minimum of 5 bits for the sequence number field in our packet header. I love this part, because it perfectly connects bandwidth utilization formulas directly to actual header design.
All right, on to Part 3, tackling the exam. Let's shift into the exam mindset for a minute and apply what we know to a really classic GATE 2006 problem. It sets up a pretty fascinating scenario. Station A needs to send a message made up of 9 packets to Station B. It's using a sliding window with a window size of 3. But wait, notice the strategy here. It's using a go-back-n flow control strategy, not selective repeat. And here is the catch. every fifth packet that Station A transmits just magically gets lost in the network, though thankfully no acknowledgments from B ever get lost.
So here's the big question. If every fifth transmission vanishes into thin air, how many total packets must Station A actually push onto the wire to successfully get all 9 packets confirmed by Station B? Seriously, take a second to think about how that go-back-end logic is going to compound those drops. Now, what's really interesting is how we can map out this resulting cascade of failures step by step. Station A sends frames 1, 2, 3, and 4 perfectly. They arrive, they get acknowledged, no problem. But frame 5? That's the fifth transmission, so boom, it drops. Because our window size is 3, Station A is still allowed to send frames 6 and 7 while it's waiting for the acknowledgement of 5, and frames 6 and 7 actually reach the receiver. But remember our rules for go back in? The receiver is expecting frame 5. When it sees 6 and 7 show up instead, it doesn't buffer them like selective repeat would. Nope, it ruthlessly discards them. So when Station A finally times out on frame 5, it has to retransmit that entire window starting from 5.
Let's follow this logic all the way to the end. The retransmission of frame 5 counts as transmission number 8. Frame 6 is transmission 9, but frame 7, that becomes transmission number 10, which is a multiple of 5, so it drops. Station A sends 8 and 9, they reach the receiver, but once again they're discarded because 7 was lost. Station A times out again and retransmits starting from 7, so now frame 7 is transmission 13, frame 8 is 14, and frame 9 is transmission 15. Which, you guessed it, is a multiple of 5, so it drops 2. Finally, Station A times out and sends frame 9 one last time. That is transmission number 16. It arrives successfully, and we are finally done. So the final answer is exactly 16 transmissions. Stepping through it step by step like this just proves the math every single time.
All right, Part 4, Contextualizing TCP.
We've just done some pretty heavy lifting with RQ math and logic traces, so let's zoom out a bit. The Transmission Control Protocol, or TCP, is basically the real-world manifestation of the mathematical ideals we just proved. While the underlying network doesn't give us any guarantees whatsoever, TCP provides a rock-solid, connection-oriented, reliable service. It guarantees in-order delivery of messages, and exactly like our sliding window examples, it uses sequence numbers and acknowledgments to recover any lost messages via retransmission.
So the crucial point here is understanding exactly where TCP sits in the hierarchy. TCP encapsulates messages into segments, and it's responsible for process-to-process delivery. It uses source and destination port numbers to make sure data gets to the correct application on a specific machine. But TCP, it actually has no idea how to navigate the global internet. It just passes those segments down to the IP layer, which wraps them up in IP datagrams. The IP layer is what uses source and destination IP addresses to handle host-to-host delivery, actually moving the data from one physical machine to another across the globe.
And that brings us to Part 5, Routing and Delivery. To build our complete picture, let's imagine how this all comes together. Process 1 sends messages down to TCP, which creates segments. These segments are handed to IP and sent across the network. But think about what happens if segment 2 suddenly goes missing in the IP layer. The TCP layer at the destination receives segment 1, but then it gets segments 3 and 4 out of order. Meanwhile, back at the source, TCP triggers a timeout for segment 2. It re-injects that specific segment back down to the IP layer, ensuring that the destination TCP layer eventually gets that missing piece, reorders the messages, and hands them perfectly to process 2. The crazy part? The applications themselves have absolutely no idea a failure even occurred.
And why is this constant reordering and retransmission so critical? Well, it's because the underlying IP network is a packet-switched network. Packets of the exact same session, whether they're TCP or UDP, do not have to follow the same physical route. They can take entirely different paths through the network, based on things like congestion and router decisions. Some might take a super fast path, some might get bogged down on a slow one, and some might just drop completely. This chaotic dynamic routing is exactly why sequence numbers, window sizes, and ARQ logic are an absolute necessity.
Which brings us to a pretty fascinating conclusion. We've proven how sliding windows and sequence numbers basically create order out of total network chaos. But think back to our math for a second. We needed 5 bits for a sequence number on a measly 1.5 megabit link. As our modern global bandwidth scales to hundreds of gigabits per second, and our transmission delays start approaching 0, the required window sizes just explode. So, will our traditional sequence number fields eventually run out of room? How exactly does modern TCP scale its window mathematics to keep up with blazing fast fiber optics? That right there is the bleeding edge of network engineering, and it's a question I'm going to leave you to ponder as you continue your studies. Thanks so much for joining me on this explainer, and keep learning.